The topic of this video is systems of linear equations in two variables. So if you'll notice the graph at the top of your notes, it says the graph below shows the supply and demand lines for a certain brand of frozen yogurt. So the red line is the supply, the blue line here is the demand. Across the horizontal axis, I have price in dollars per half gallon. And over here on the vertical axis, I have number of half gallons. The first question is, at what price does the supply equal the demand? So where does the supply equal the demand? And I think you can see it is at this point right here where those two graph lines cross. So at what price does that happen? I'm going to take this point and follow it down to my price, and it appears to be $4. So at $4 per half gallon, the supply equals the demand. And then it says, for how many half gallons does supply equal demand? So this time at the equal point, I'm going to follow it across to my vertical axis, and it appears that it is at 300 half gallons. This graph and the equations that represent those two lines are called a system of equations, meaning just more than one equation at a time. So let's look at example 1, and the first thing we're going to do with the system is we're going to decide whether an ordered pair that we are given is a solution to that system, meaning, let's go back to our graph. This point right here is a solution to whatever the equation was for the supply line, and it is a solution for whatever the equation was for the demand line. Now, I didn't give you those two equations. I didn't really want to. So let's look at this example and see if this point is the solution to these two. Well, the only logical thing to do is to take that point and substitute it into each of the two equations in our system and see if it checks out. So in the first equation, I would put in 4 for x, 2 for y, and it definitely checks out. So that point definitely is a solution to that equation. But that doesn't mean it's a solution to the whole system. So now let's check it out in the second equation. 4, take out the x, put in a 4, minus 2, does that equal 14? 16 minus 2 does equal 14, so this ordered pair is also a solution to that equation, meaning if it's a solution to both, it is a solution to the system. So we would say yes, it is a solution to the system, meaning it solves both of them. All right, let's look at the next one. Example B, I have again a system of equations, and we're going to check out the point -1, 7. So in the first equation, that would give me 3 times -1 plus 2 times 7. Does that equal 11? Does -3 plus 14 equal 11? Yes, it does. So it solves that equation. Now we're going to check the second equation. Take out the x, put in a -1, plus 5, take out the y, put in a 7. Does -1 plus 35 equals 36? Oops, 36, sorry. It does not. So this point is not a solution to this equation. Therefore, it is not a solution to the system, even though it was a solution to the first equation, because it was not a solution to the second equation, it's not a solution to the system. So in order to be a solution to the system, it has to solve both equations. Very simple. Looking at the bottom of your notes, you're going to see 3 graphs here, and these are the 3 possibilities for the number of elements that would be in the solution set of a linear system in two variables. So here's what can happen. If I graph my two lines, like I did up here with the frozen yogurt, the supply and the demand, if I graph my two lines, they can intersect at one point. So that is their intersect point, which is the solution point of the system. So if there is one solution, it means it's a consistent system, just meaning there was a solution, but the equations are independent. meaning the lines are two different lines. And I'm not interested if you know these two words as much as I am interested in you understand the possibilities that can happen. The second possibility is that you have two lines in your system, but when you graph them, there is no solution. And the reason that there's no solution is that my lines are parallel. Parallel lines don't intersect. So there's no point that would solve the blue one and the red one. Remember, it's an and. We call that an inconsistent system because there's no solution, and they are independent because the lines are still different lines. A red line and a blue line. Finally, the last thing that can happen is I can graph my red line, and when I go to graph my blue line, it lies right on top of the red one, making purple. So you see what I did there with the colors? Red and blue makes purple. So we would say there are an infinite number of solutions here because at every point on that line, the red and blue, or purple, share the same point. So they share those solutions. So there's infinite solutions. They are consistent because there is a solution, but they are dependent equations because the lines are not separate. They lie on top of each other. So you have your options of one solution, no solutions, or infinite solutions.